Okay. So last time we talked a lot about, so what did we talk about last time? Recap? We talked about vectors, right? So we've become more, we've transitioned away in a bit from just dealing with matrices, matrices, and matrices. And now we're looking at things from a more vectorial perspective with vectors. And we understood what vectors were, right? We have, they're also considered like n tuples. So a vector is an n tuple in r-dimensional, in Rn space, a coordinate that has a point in an n-dimensional space that has n coordinates to it, right? And we talked about how to add them, subtract them using the parallelogram rule, also known as the tail to tip method. Of adding, subtracting vectors. So when you have a particular vector, when you have two particular vectors, and you want to add them or subtract them, you can construct a parallelogram. And in doing so, you have these two diagonals. So one of them would be the resultant, right? As some of you may have seen in your physics courses, that's the sum. And the other vector, the other diagonal, would be the difference. So if I have something like this would be u minus v. Okay, so we talked about adding and subtracting. We also talked about scalar multiplication of vectors, right? We can either minimize or maximize a vector along the same direction. We also talked about the linear combinations. A linear combination, very important concept in linear algebra, especially when we talk about vectors, right, is a sum of scalar multiples of vectors. In other words, W can be, if I have a vector W, let W be a vector in Rn. And we can rewrite this as a linear combination of other vectors suppose n of them. Then when I add the scalar multiples of these vectors in a particular way, I can represent this new vector W as a linear combination. So here we would say W is a linear combination of the vectors v1, v2, all the way to vn, right? That's what that means. So whenever we have something like this, written in this way, expressed in this fashion, we say that that vector W is a linear combination of the vectors v1, v2, vn. All right. We also talked about the standard basis right? The standard basis in R3, E1, we write it as I hat, E2, we write it as J hat, and E3, we can write it as K hat, right? So we have another representation of the standard basis vectors in R3. We also talked about a very important concept called the norm. Very important about vectors. So the norm is the length of a vector. So suppose V is a vector in Rn. Then we were given the notation for the norm, which is two absolute value signs you can think of on each side of V. And we saw that this equaled the square root of V1 squared plus V2 squared all the way to Vn squared. So it's the generalized version of the Pythagorean theorem, which we explored last time. Okay, on top of that, the norm, we also talked about the unit vectors or normalizing, right? So the unit vectors, whose norm equals 0, 1. Vectors whose norm equals 1. So a little example of that, let's say you have the vector 3/5 and 4/5. Then we take the norm of this and you square each component and you add them together. We get 1. And then we finished this whole little world of unit vectors by talking about normalizing. So let's say I'm given a vector that is not a unit vector. So if I have a vector that's not a unit vector, how do I make it? How do I transform it? So let a V, pardon me, be a vector of non-unit length. In other words, the norm of V is not 1. Then U is what? 1 over the norm of V multiplied by V. Then U is a unit vector in the direction of V. So you can give me any vector whatsoever, and I can multiply that vector by a certain scalar, which is this one 1 over the norm. And in doing so, I have shrunk it in a way or maximized it in a way that would create a unit vector. Okay, so that's what we discussed last time in a nutshell. And so now I want to just touch a bit more on linear combinations. I just want to do a few examples. So one of these examples is write write negative 4, 4, 4 as a linear combination. Let me call this W, okay? Just to give you some notation here. So let W be the vector, negative 4, 4, 4, as a linear combination of vectors. We'll call it V1. V1 is 2, negative 1, negative 1. V2 is 2, 0, negative 1. And V3 is 1, 0, negative 1. Now, what does this mean again? In a sense, whenever you're given vectors such as this, right? We're given one vector and you're given a set of other vectors for which you want to find a linear combination of. Really the goal of this is find the scalars C1, C2, C3 that expresses W as what we've mentioned earlier, C1 V1 plus C2 V2 plus C3 V3, or in a shorter notation would be the summation from 1 to 3 of CI VI. Right, that's what I want to figure out. I want to figure out what is C1, C2, and C3. That's really what I want to figure out. That's my goal. If I'm able to do that, then I found the linear combination. So let's write this out. So this becomes negative 4, 4, 4 equals C1. This becomes what? 2, negative 1, negative 1 plus C2, 2, 0, negative 1 plus C3, 1, 0, negative 1. Now, I don't know if you see this yet, but what does this remind you of? What kind of equation can I transform this into? Baldwin.
It reminds me of the standard basis.
The standard basis, yeah. These are bases, but we haven't talked about general bases yet. We only talk about standard bases. But what else does this remind you of? So this is where you kind of have to think about what does this actually mean on the right side? What am I actually doing here? So if I multiply the vector, right, by their specified scalar, what would this look like? Wouldn't this look like 2C1, negative C1, negative C1 plus 2C2, 0, negative C2 plus C3, 0, negative C3? And if I add these, you can think of them as matrices, 3x1 matrices, then I add them by components, don't I? So doesn't this become 2C1 plus 2C2 plus C3? This becomes negative C1. This becomes negative C1 minus C2 minus C3. This is negative 4, 4, 4. System of equations. That is right. Do you see that? So this in reality, this becomes what? Negative 4 equals 2C1 plus 2C2 plus C3. 4 becomes negative C1. 4 becomes negative C1 minus C2 minus C3. And then, of course, finding C1 is quite straightforward. Then you can plug that in here, you can plug that in here, and you can solve that system in that fashion. But the important thing to notice is that this is a system of equations with 3 unknowns and 3 variables. So then what is this really also can be written as what? My C1 can be considered like X, C2 can be considered Y, C3 can be considered like Z. And we've seen these equations before. So we can create a coefficient matrix, can't we? 2, 2, 1, -1, 0, 0, -1, -1, -1. And then the column vector would be C1, C2, C3. And this will equal the column vector -4, 4, 4. Now, this should make sense if you guys remember what matrix multiplication was also expressed as. If you guys remember, matrix multiplication is also a linear combination of the columns. So when you do perform a matrix multiplication of this sort, another way to represent this is this here. Because I just showed you how algebraically we went from here and we went all the way down to here. So immediately next time, the moment you see this, you should immediately think, oh, this is the first column of the matrix, second column of the matrix, third column of the matrix, for which I can create a matrix equation of this sort, where these become the columns of the matrix. These are the scalars that I'm looking for, which would result in the vector that I have it equal to. So I can create this matrix equation now. I can call this A, I can call this X, and I can call this B. So then how do I find X? Right, this is something that you had in your exam as well. How do you find X? Well, X is equal to the inverse of A multiplied by B, column vector. Now at this point, it's okay to use your calculator for this because we get the point. We get the point that we need to find the inverse of A and multiply it by the column vector B. So I'll do that on the calculator. If I have it open, let me just the application. Okay. So in your calculator, so here we have second matrix. I'm going to a 3 by 3.
What is this one?
Okay, so then here we have 2, 2, 1, -1, 0, 0, and then -1, -1, and lastly -1. So that's going to be my matrix. I'm going to call it in my calculator will be B, but in my notes it will be A. And then I'm going to use the C matrix name here for the 3 by 1 matrix. And this will be called -4, 4, 4. So what I'm looking for to do is to find the matrix that I just defined, the coefficient matrix. I take the inverse of that matrix, multiply if it exists, and it will, multiplied by the column vector that I just defined myself. And so I actually get the column vector is -4, 4, -4. So what I want you to see, so the point, okay, so I solved it, right? Solved. So my solution is what? C1 is -4, C2 is 4, and C3 is -4. That's what I found. So once I found this, I am finished with the sense of, in the sense of that I found the linear combination of C1, C2, C3. So the linear combination, all I had to do was replace C1 with -4, multiply that. If I have 4 of these V1s and I add another 4, well, I have -4 of those C1s plus 4 of these V2s, I got a -4. So this here would be the linear combination. And what I want you to see, the connection, is that in the beginning of this semester, we've been dealing with how to represent linear systems of equations into matrix equations and solving these systems for X, Y, and Z, right? Now we're transforming this problem into a different problem. The solution, the steps of the solutions are identical, but the problem now is different. The problem is not, can we solve the system of equations? The problem is, can we find a linear combination of these vectors? Now, you see how posing the problem sounds different, but inherently it's the same. So that's what's really nice about linear algebra, is that you're able to represent problems in different fashions, yet the solution is identical. So I want you to make sure that now you're able to see the connection between systems of equations that we've been dealing with in the beginning to linear combination, the question of linear combinations of vectors. And that's the connection you have to now transition towards. So now we're going to be dealing with this a lot more than system of equations. Now, system of equations is going to be a thing of the past. It's going to be something that you're like almost a trivial matter because all you have to do is create this matrix equation and you got it. But now this idea of linear combinations becomes more rich. Okay, so that's how you approach these problems with linear combinations. Okay, and so in the same token, right, that we've talked about these things. So what if I have another example in a similar vein, okay? So suppose I have an augmented matrix. And this augmented matrix looks like the following: -1, -1, 2, -4, 2, 1, 4, 3, -3, and then we have this augmented part, -3, 4, -3. And what we do is we perform Gauss-Jordan elimination and get the row reduced echelon form. And we get this, we get the expected identity matrix for the 3x3 submatrix. And then the column here becomes something strange like this. Now, I'm not going to make you, so now I'm not, the question is not, can you perform the row reduced echelon? Can you perform the row operations upon this matrix to get to this point? Like that no longer becomes a goal of ours. Now I'm giving this to you. Now, how do you interpret this? What would be the interpretation? Of above in terms of linear combination of vectors? I'm going to put it in parentheses, column vectors, because we're talking about the columns. What would be the interpretation above? So again, I'm trying to help you transition from considering things from the perspective of systems of equations to column vectors. So normally this would be an equation, right? This would be some equation. We would have negative x plus negative 4y, or I should say negative x minus 4y plus 4z equals negative 3. Then this would be x, this would be plus 2y plus 3z equals 4, so on and so forth, right? That's normally how you would interpret it. So then Sam says the fraction on the right represents the values for x1, x2, x3. That gives us the values, right? That gives us the values, negative 3, 4, negative 3 from the system of equations. Right. So these are the solutions, correct? So this would be the solutions, the solution for the system of equations, but then how do I relate that with this idea of linear combinations? A inverse times negative 4, 3 equals x bar. That's right. Okay. So what is x bar? And what is, so this here, you can interpret this as the matrix A. This here, you can interpret this as the column vector B. And this here is the column vector X, which is a solution. But that still doesn't explain what is the linear combination interpretation of this. So in terms of system of equations, I know you guys understand that we found the solution to the system of equations that has these equations, right? But then what is this also, how can we also consider this? These are what? Beyond just the solutions of the system of equations, what are these? Numbers or fractions. So let me write this out then. So far this is A, right? A multiplied by AX B. And we got 1, negative 4, 4, negative 1, 2, 3, 2, 1, negative 3. This is A. Then I'm multiplying this by an unknown. If you want to call this X, Y, Z, so be it. Normally though, we can write this as X1, X2, X3, or C1, C2, C3. And this becomes negative 3, 4, negative 3. Okay, so this is the equation, and we apply A inverse to get AX. We apply A inverse to get X, and we did that. And we showed by row reduced echelon form, we showed that X, X1, X2, X3 we know that this equals negative 55 over 23, 26 over 23, and negative 5 over 23. We know this. But what I'm asking is, what does this represent in terms of linear linear combinations? What I just found, what these are the scalars associated with each of these columns. So that when I add these up, it gives me this. So I can rewrite this. So this can be interpreted as a linear combination. If I get negative 55 over 23 of 1, negative 1, 2, I add that to 26 over 23 of negative 4, 2, 1, minus 5 over 23 of 4, 3, negative 3. This adds up to negative 3, 4, negative 3. Do you guys see that? This is my V1, V2, V3. This is my V2, and this is my V3. This is my vector W. Do you guys see that? And then this can be considered my X3, as we've mentioned. This is here my X2, and this here is my X1. So the X1, X2, X3, or the X, Y, Z, the C1, C2, C3, these are scalars for the respective vectors, so that now this equation here can be, this matrix equation can be interpreted as finding the scalars that would provide the linear combination of the vector of the columns of this matrix that gives us the column on the right, vector on the right. That's the idea, guys. So you see this? This is what this represents. This augmented matrix and its row reduced echelon form, instead of just saying, oh, this is a solution of the system of equations that I had, now you can say these are the scalars for which the column vectors can be multiplied by so that it gives us a linear combination of that column B. And that is the new way to interpret all of this. Any questions about that? Does that make sense? Yes or no? Yes. Great. Great. Okay. So that's understood. Okay. So we talked about vectors, linear combinations of vectors, and the like. We're going to continue with vectors. We're going to touch upon and head into a very important operation called the dot product. Without the dot product, I don't know what we would do with vectors. So let's see how a dot product is defined. So definition, if you, I'm gonna call it V and W. If V and W are non-zero vectors, in Rn, you know what, I'm just gonna write it as in R2 or R3. And theta is the angle between V and W, then we call it the Euclidean. We talked about this before, right? The Euclidean distance is the way we defined it using the square root of the sum of the squares. So the Euclidean dot product is denoted and defined as if we have V multiplied or dot product. So this dot literally means dot product. It is not multiplication in the sense of multiplying two numbers because we don't have two numbers, we have two vectors. So the dot product is only applied for vectors only, nothing else. So the dot product itself is only between two vectors. So the dot product is defined as the norm of V multiplied by the norm of W times the cosine of the angle. That's how we define dot product, or particularly Euclidean dot product. Okay. Now, this is not the best. Well, this is one definition. There's actually another definition for a dot product. And we'll see how that can play out. So what does this look like? How can I interpret this visually? So visually, you consider this as two vectors in space, and let's consider this to be in the third dimensional, in the R3. So we got X, we got Y, we got Z. And we have some vector out here. And we have another vector out here. So I'm gonna call this V, and I'm gonna call this W. And I have this vector here, connecting these two tips. And the angle between V and W, this is theta. And so this would be what? This would be, this would be W minus V. Right, this is my vector. The difference between W minus V is this vector here. What did I just create? I created a triangle. Now, does anybody remember what is that law in trigonometry that relates the sides, the three sides of a triangle, of any triangle, with one of the angles? Probably saw this in pre-calc. You guys remember? The law of blank. The law of powers. No. There are laws of exponents, law of powers that does exist. But again, what's the law in trigonometry that relates the sides, the three sides of a right triangle with one single angle? Adjoints. Yeah, it's a good one. It's the law of cosine. You guys remember law of cosine? And the law of cosine, it's the generalized version of the Pythagorean theorem. So again, this Pythagorean theorem comes up a lot. I wonder if Pythagoras, he probably didn't even consider the implications, the broad scope implications of his theorem. So the law of cosine states the following: the angle, the side opposite the angle that you're given, when you square this, that's going to be equal to the side squared plus the other side squared minus the product of these lengths multiplied by the cosine of the angle. So I know I may be saying all these things and you're like, what are you talking about? Well, that is the law of cosines. So I'm gonna call this squared. This is V squared plus W minus 2 times the length of V multiplied by the length of W multiplied by cosine theta. This is called the law of cosines. But of course, now we have this new kind of notation with the norm of vectors. So again, this is a vector. This has a length. And I'm taking the length of this, which is the norm, I'm squaring that. Taking the length of this, the norm, squaring that, plus the length of that. So if you notice, if you take away this here, this cosine term, if you take that away, you get the Pythagorean theorem. But the law of cosines is applicable not just to the right triangle, because the Pythagorean theorem only is applicable for the right triangle. The law of cosines extends this idea of Pythagorean theorem to all angles. So if this is cosine of 90, cosine of 90 would be 0. That's why it goes away. But let's say this angle is not 90. You can still relate the three sides together using the law of cosines. Okay, so what we're going to do is we're going to do a little bit of algebra. So we're going to make it a little bit, we're going to do some switcheroos here. Make this a little smaller here. So what I'm going to do is I'm going to move this term on the left side and move this term on the right side. So I'm gonna go this way and this will go this way. So what happens, this becomes 2, the norm of V multiplied by the norm of W times cosine of the angle is equal to norm of V squared plus the norm of W squared minus the norm of W squared minus V squared. No, norm of W minus V squared. Do you guys see that? That's all I did. It seems familiar now. Very good. And then what I'm going to do is I'm going to divide out the 2 on both sides. So when I divide out the 2, this is what I get. I forgot it's squared there. And one thing I should just say, just for like the let statements, right? These let statements actually are very useful. I'm gonna call V, V1, V2, V3, whatever that is, an arbitrary vector. I'm choosing an arbitrary vector W, W1, W2, and W3, okay? So let that be the case. Then if that's the case, then I can represent this triangle here using V, W, and W minus V. And then I can represent the sides of this triangle with the angle that I'm given and between V and W. So remember, this angle is between V and W. And I can represent it using an equation that's applying the law of cosines. Now, what am I trying to get at? Well, I just defined the definition for the dot product of V and W is the product of the length of V with the length of W times the cosine of W, a cosine of the angle, which is the angle formed between the vectors V and W. So I just found that this is equal to the dot product, the way it's defined. So V dot W is what I have on the left, on the right, 1/2 squared plus this squared minus this squared. So this looks complicated, doesn't it? But what is the norm of V squared? What is the norm of V squared? Well, remember, what is the norm of V? It's the square root of V1 squared plus V2 squared plus V3 squared. But when I square something that has a square root, doesn't that cancel? So in reality, what do I have now? I got 1/2 of what? V1 squared plus V2 squared plus V3 squared. And then what's going to happen with the norm squared of W? Same thing. So I'm adding this to it. Whoops, I was right, 3 squared. Now, what is W minus V norm squared? What is that? I'll put this in different color. So what is that, guys? What is W minus V squared? It's W1 plus W2 plus W3 minus V1 minus V2 minus V3. So that is W. Well, I think you can write this a little bit clearer. W minus V is W1 minus V1, W2 minus V2, W3 minus V3. But I'm taking the norm squared of that. So what is that going to produce? That's going to produce W1 minus V1 squared plus W2 minus V2 squared plus W3 minus V3 squared. Because I get rid of the square root, right? When I square this. So there's a lot of squares, guys. Is that clear? So that's what I get here. So let me take this guy. Let me yellow. Let me make this smaller. And let me bring this over here. So this entire thing here, this is associated with this. This here is this here. And this here is this right here. Okay? So I've just unpacked what these norm squared terms are. Now, why did I do all of this? I'm trying to get to somewhere, right? So this becomes 1/2. Now, what happens here with the W1 minus V1 squared? What do I get? So this here will still be around. But then I got W. Repeat which part, Baldwin?
Sorry for the background noise, but I was referring to the previous, like the last line. The V dot W.
V dot W, right?
Yeah, like what it equals to. I was kind of confused.
Right. So V dot W comes from this here, right? And this comes from this portion here. This is the law of cosines, and all I'm doing is I'm rewriting it so I get V dot W, because what am I trying to show? I'm trying to show another definition for the dot product. And so I was able to recognize, hey, look, in moving that around, this expression is exactly what V dot W represents. This is the way the dot product was originally defined, as we defined it here. V dot W is the product of the norms of the vectors multiplied by the cosine of the angle. So now I can replace this with V dot W. And now I have all this stuff here just by the algebra of moving things around. And now this here, I'm able to write it as a sum of the squares of V, of the components of V. Remember, V was defined as V1, V2, V3, that vector. And W is defined as W1, W2, W3. So the norm of V squared, the norm of V is this expression here. So the norm of V squared is the same thing underneath the square root, but without the square root, because when you square the square root, that cancels out. So the norm of V squared is just the squares of the components of V. The norm of W squared are the squares of the components of W. And now that's taken care of here. This is taken care of here. And now that last piece here, I'm trying to find the norm of W minus V squared. So what's W minus V? Remember what W minus V represents? It represents that side opposite the angle theta. What is W minus V? It's simply just subtracting W1 minus V1, W2 minus V2, and W3 minus V3. That's what this represents. And so finding the norm of that squared means, hey, do the same thing. Take the first component, square it. Take the second component, square it. Take the third component and square that. And that's why I get this on the end. Do you see that? So I am subtracting by this expression, which is represented by this product, this sum of products, sum of squares.
Yeah, explained enough. Thank you, Professor.
Yeah. And so now let's unpack that even further. What does W1 minus V1 squared become? W1 squared minus 2W1 V1 plus V1 squared plus W2 squared minus 2W2 V2 plus V2 squared plus W3 squared minus 2W3 V3 plus V3 squared. So all I did was I unpacked the squaring of these binomials. These are binomials. And then I have this, let me just put this around like this. And now I can distribute this -1 to every single term, right? And so what happens? V1 squared, V2 squared plus V3 squared plus W1 squared plus W2 squared plus W3 squared minus W1 squared plus 2W1 V1 minus V1 squared minus W2 squared plus 2W2 V2 minus V2 squared plus W minus W3 squared plus 2W3 V3 minus V3 squared. What happens? Cancellation galore. We got V1 squared, V minus V1 squared. We got V2 squared, we got minus V2 squared. We got V3 squared, we got minus V squared. We got W1 squared, we got minus W1 squared. We got W2 squared, we got minus W2 squared. And we got W3 squared, we got minus W3 squared. So what's left? We got 2W1 V1 plus 2W2 V2 plus 2W3 V3. But I'm multiplying this whole thing by a half. So that all those twos cancel out as well. So what did I just figure out or show? I showed that V dot W, and when I interchange the numbers, the components here, I can write this as the product V1 dot times W1 plus V2 times W2 plus V3 times W3. So this is another definition for the dot product. I remember briefly someone mentioned this term dot product when we talked about matrix multiplication. And I said, yes, this is called the dot product, but we just went about what that matrix multiplication step implied. But for every single time we do the row multiplied by the column, we're applying the dot product. And so the dot product, as you can tell, only can occur between two vectors of the same length or of the same number of components. You wouldn't be able to have different size vectors and dot product them, because then you wouldn't be able to pair each component together to multiply them and so to add them. So dot product can only occur, only can be applied to vectors with the same number of components. Okay. This is the more familiar way of defining dot product. But this is the more, and I would say geometrically inclined way of representing the dot product. Does that make sense? So that's another definition. Okay. Okay. So if we have this clear, and I kind of stumbled upon this a bit with the derivation of it. So just keep a note about norms, right? So if we have the norm of V, remember what the norm of V is, right? It's V1 squared plus V2 squared plus dot 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 Vn squared. But what is V1 squared? Isn't it V1 times V1 plus V2 times V2 plus dot 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 Vn times Vn? But didn't I just define the dot product between two vectors as the products of their components being added to one another? So in this case, what am I dot producting here? How can I rewrite this as a dot product? Instead of writing V1 squared plus V2 squared dot 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 Vn squared, how else can I write this as a dot product between what two vectors?